We're going to go over how to find the formula of a power function that goes through two given points. We were talking today in class about power functions, and we broke down their behavior for positive and negative integers, even versus odd, and for non-integer rational exponents as well. So if I now have 2 points that I know are on a power function, I know that a power function has the form y equals x k to the p, where p can really be any number. They haven't told me what kind of a power function it is. If I quickly sketch these points, I might be able to have some idea what's going on. Here's 432, here's 1/4, 1/2. So the function has to go in some sort of a pattern like that. I'm not sure what's happening here to the left of the y-axis, or if it turns around or anything like that, but certainly I can see as x gets bigger, y gets bigger. So I would want to make sure when I error check that my function makes sense. So essentially, I really just have to find two parameters. So this is very similar to when we did exponential functions. I need to find the constant k, and I need to find the power p. So since I have 2 points, I simply plug those in, and I have a system of equations in 2 variables. So the first part tells me, I'll call this equation 1, 32 would equal k times 4 to the p, because x is 4, y is 32. And then what I'll call equation 2 would tell me that 1/2 should equal k times 1/4 to the power p. So I can use either some combination of substitution or linear combination. I'm going to use linear combination where I'm basically going to divide both sides of equation 1 by equation 2. So in other words, I started out with that I had 32 equals k times 4 to the p. I'm on the left side going to divide by 1/2, and on the right side divide by k times 1/4 to the p. I'm basically dividing both sides of the equation by the same thing because 1/2 and k times 1/4 to the p are equal. So on the left side we get 64. Then notice here our k's reduce, cancel out as we sometimes say, and I'm left with 4 to the p over 1/4 to the p. It's frequently useful when working with exponential equations to rewrite everything with the same base if possible. And in this case, that is possible. I can rewrite 1/4 as 4 to the negative 1, and then that is to the p, right? I replaced the 1/4 here as 4 to the negative 1. Now just using all of my laws for exponents, we have 4 to the p on the numerator, 4 to the negative p in the denominator. When I'm dividing with the same base, I add the exponents. So p minus negative p is p plus p, or 2p. So in other words, we end up with 64 is equal to 4 to the 2p. Again, before I get super excited to take logarithms of both sides, I realize I can rewrite those with a common base, which is always going to be the easiest, most efficient way to solve the problem. So 64 is actually 4 to the third. So 4 to the third equals to 4 to the 2p. The only way that's true is if 3 is equal to 2p, which implies p has to be 3/2. So now I have one of my two parameters. All that's left to find is k. So now I can plug that in to either equation that I want. Remember, we now know that we have something in the form y equals k, right, kx to the p, and we just found that p is 3/2, so kx to the 3/2. So now I substitute either point in to just solve for k. I'm going to use the whole numbers. That seems like I would be less likely to make a careless error. So y is 32, x is 4, and I just want to solve for k. So I'm going to simplify this. Some of you, I assume, can do this in your head a little bit more quickly, but I'm going to think of 3/2 as 1/2 times 3. So then k to the 4 to the 1/2, is 2. So I have 2 to the third, and 2 to the third is 8. So dividing both sides by 8, we get that k should equal 4. So our final answer, our goal, remember, was to find the actual equation. So our equation here should be y equals 4. That's what we found k to be. X to the 3/2. That's what we found p to be. And certainly I can check it's an exponent larger than 1 with a positive lead coefficient. So as x gets bigger, y should be getting bigger, certainly for positive x, which is what we expected. And if I do a graph of it, we get something that looks like this. So here we can kind of trace along the graph and see that in fact, here's 432 is the solution. It's the solution right there. So 432. And somewhere over here is going to be our 1/4. 1/4, 1/2 is right there. So this particular power function certainly seems to fit that data. We chose a power function, of course, because they said specifically to find a power function for those 2 points.